So, does anyone remember what I told you last week was the most important thing you would learn that day when we were talking about pure imaginary numbers? Anybody have any recollection of what that was? What those things were that I said were the most important thing you would learn that day? Well, at least you're honest. I can't write the letter N today. So we were talking about I, right? The imaginary unit. I equals I. Well, that's not the most important thing because everything equals itself, right? I think I know what you're talking about, though, Mashka, when we were talking about the powers of I. Yeah. What I said the last time is that I equals the square root of -1 and that I squared equals -1. I do appreciate everyone that tried on that. But right here is the most important piece of information that you can have when you're dealing with complex numbers, right? It's knowing what I equals. And we did things in that sense where we talked about, like, if we had the square root of -4, we could pull that out as an I, and then it would just be the square root of 4, and we would get plus or minus 2I out of it. You guys remember all of that? Kind of, is that coming back to you? I know we've had a weekend off. It's easy to forget. We need to be brought back into that mindset. Today we're moving into the complex number system itself, which is like 2I, I or 2I or -3I, anything like that we refer to as pure imaginary numbers. And pure imaginary numbers are part of the complex number system. But a complex number takes the form of A, either plus or minus BI. So it's a real number plus or minus a pure imaginary number, right? And this is what we consider a complex number. This, by the way, is the standard form of writing a complex number. If you enter it in a different way in Delta Math, which is where your homework will be for the next 2 assignments, it will be in Delta Math, which is nice because you don't have to show any work for Delta Math. Make sure that you have it in this form where you've got the real component plus or minus the imaginary component, because I don't know that it'll let you have it right if it's not written in that form. The good news is on Delta Math, you can keep going till you get 100% anyways. So if you mess it up like on one and it shows you how to do it, it's not like you're going to lose points on it. Just do an extra problem. Today, the stuff we're doing is fairly simple, right? We're doing adding and subtracting complex numbers and multiplying. And that is the gist of it. And part of that is that it's going to take me a little time to explain to you the complex number system. When math started, when you first learned math, you learned counting numbers, right? How did you start when you were counting? What was the first number you started with when you first learned math? Uno, right? Everyone started one. You count on your fingers, 1, 2, 3, 4, 5, right? We call those the natural numbers, right? The natural numbers are the set of all numbers starting with 1, 2, 3, comma, and they go on forever and ever, right? They are infinite, right? You can have natural numbers forever and ever. You will never run out because you get to the end. If there was an end, then you could always just add one more, right? And so natural numbers are an infinite set of numbers, right? and they're contained here. But then we got to this point where we had none, and we needed something to represent none, right? And so we came up with this system called the whole numbers, which is exactly the same thing as the natural numbers, only we start counting now at 0, right? But it's still this infinite set. It still goes on forever and ever and ever, right? Except for that this infinity is a little bit bigger than the infinity that is the natural numbers. Sort of. Not that infinities can be bigger than the other, but kind of they can, right? How many bigger is it? 1, right? The only difference between the infinity that is the natural numbers and the infinity that is the whole numbers is that for natural, we start counting at 1. And for the whole numbers, we start counting at 0. If you think about the natural numbers, everything in the natural numbers is within the whole numbers, right? It is like a subset of the whole numbers, right? Everything in the natural numbers is concluded there. Then we had to start thinking about, well, what's on the other side of 0? Like, what's less than 0? If I owe you money, I have less than $0, right? If I have $5 and I owe someone $7, I really have negative $2, right? And so we had to come up with this negative space in numbers, right? Like, how do we have less than nothing, right? And we came up with the integers. Now, the integers, for some reason, we use the letter Z to identify them. Now, I know why we don't use I, because I was taken. I don't know why they started using Z. But the integers are contained, they have all of the negative numbers all the way to infinity. So we go like -2, -1, 0, 1, 2, and then they have everything else in both directions. So if you think about this in terms of a set, you can see that the set of integers encompasses the whole numbers, which encompasses the natural numbers. Does that make some sense to you guys? I know you've seen like the organization of numbers, but I kind of like to present it as a whole thing, right? Then on top of that, we also have fractions, which we haven't discussed, right? We had all of those little infinities between numbers. Like if we look at a number line and say I have the numbers 0 and 1 right here. How many numbers are between 0 and 1? Infinite, right? Because fractions can keep getting smaller and smaller and smaller. It's getting infinitely small, but there's still an infinity just between these two numbers, right? And they're called fractions. We refer to those as the rational numbers. I don't know why I'm writing them as R, because they aren't. We refer to them as the set of Q. The reason we use Q, I actually know. Unlike Z for integers, I know why we use Q for rational numbers, and that all of these numbers can be written in the form of a fraction, which fractions are division problems, right? Even the fraction symbol represents division, right? If you look at the fraction symbol, the division symbol, it's saying this number divided by this number, right? It's actually a fraction is what the division sign is. So this is everything, right? It's going to have like -4/3, -1, -1/2, 0, 1, 3/2, on and on forever and ever, right? So you could see that this set of rational numbers, our Q set, it has all the fractions. Ooh, that was weird. We'll have to get rid of that. We'll make that prettier. But it encompasses the integers, it encompasses the whole numbers, and it encompasses the natural numbers, right? They are all part of that set. I'm not going to fix it again. Well, all of those numbers are part of what we call the real number system, right? And up until this point, we always counted everything in terms of real numbers, right? The only other thing that's part of the real number system is what we call the irrational numbers. And you would know what those are. They're like pi or the square root of 2 or the square root of 3, things that have these repeating decimals that go on forever and ever. You would recognize them if you saw them, right? They're those weird numbers. And for the longest time, for like centuries, we thought that that was all that existed, was this real number system. And then we discovered these imaginary numbers. Like we found a need to be able to calculate negative space, and we came up with imaginary numbers, and we found that there's this whole other number system that we needed to define the world. And it was the complex. Oh, that is the worst rectangle anyone has ever made in the history of making rectangles. It's not even going to help me out on that one. It doesn't even recognize it as being a rectangle. It's that bad. So this complex number system includes our a plus bi, right, where we have our real component and our imaginary component. And then it just has our I as well, our pure imaginary, right? That's pure imaginary. And this is just complex. We just call this a complex number, right? Where it's got both an imaginary and a real component. I will get more into the nitty gritty of the complex number system the next time I see you. For today, we're just going to talk about adding and subtracting complex numbers and multiplying. And the next time I see you, I will do dividing and complex conjugates. And then we'll be done for the semester. We won't have any new information. Your homeworks, the one you get today and the one that I give you guys on Thursday when I see you, neither of them should take you more than 10 minutes. Like we're not doing any kind of rocket science here. We're just kind of introducing the complex number system. And you'll see that it doesn't work. It's not as complex as its name might suggest, right? As long as you remember those two key elements, right? That I equals the square root of -1 and that I squared equals -1, right? Still the two most important things. Otherwise, when we're dealing with these things, all we have to remember is to treat I like a variable for the most part, right? Treat it like it's X. So when we are adding and subtracting complex numbers, subtracting. If I have, for example, -11 plus 3i plus 9 plus 2i, I can literally take everything right out of the parentheses. I could write this as -11 plus 3i plus 9 plus 2i, right? And then all I would ever have to do with this is combine our like terms. Starting with our real numbers, I would go, okay, well, -11 plus 9 is just -2. And then 3i plus 2i is plus 5i. So nothing too difficult, right? It's literally just like dealing with a problem that has a variable in it, right? Subtracting is slightly more difficult, just like when we're subtracting binomials is a little more difficult. If I had, say, 7 minus 2i, let's put a dot up there so you can tell it's an I, minus 2 plus 6i, it works very similarly to addition. This first part can come out. I could write this as equals 7 minus 2i, but we have to distribute this negative to each part. So that would be minus 2, but it is also minus 6i. And ultimately, all it serves to do is change the sign of everything that comes behind it. So then I'd combine my terms, right? I have 7 minus 2. Well, that's just 5. Minus 2i minus 6i is minus 8i. So it's not particularly difficult, right? We haven't jumped into anything that's super hard. Even if I threw in like an extra deal, say I threw in 6i minus 14 minus I plus 5 minus 3i, right? I can still look at this and I can go, okay, well, I have 6i. That's not getting touched at all, right? There's nothing on it. I have to distribute this negative. So I have negative 14. Notice this is a negative times a negative. It becomes plus I. And then this one has a positive in front of it, so we can just rewrite it. And now we can combine our like terms. We do our real numbers. Minus 14 plus 5 is negative 9. And then we're going to combine our i's. We have 6i plus I. Well, that's 7i. Minus 3i is 4i. Everyone good with that? Do you need more examples of that one, or do you feel fairly confident with it? Like I can move on. I feel like the only piece of information I really gave you is that you have to remember that if you have a negative in front of that parenthesis, you have to distribute it to each piece, right? Will you mess it up? Absolutely, you will. And that's okay, right? You'll figure out what the problem was and you'll fix it. That takes care of adding and subtracting. And I told you we're only doing those things today, right? Adding and subtracting and then multiplying. So the last thing we have to talk about now is multiplying complex numbers. This is really where this piece of information is going to come in handy, that I equals the square root of negative 1 and that I squared equals negative 1. This part specifically, we're going to use a lot. So if I have an example, say, I don't know what I think this is number 4, example number 4. If I have 2i times 8 minus 3i, I'm going to go ahead and distribute this just like I would anytime I'm multiplying something times its parentheses, right? We know that we would multiply this times this and we get 2i times 8, which is 16i. And then we would multiply it times the next part, and we'd have 2i times 3i. Well, 2 times 3 is 6, and then I times I is I squared. But what do we know about I squared? What does it equal? I mean, everyone should be answering that because it's written right here. Right? It equals negative 1. So I have to adjust that, right? I have to go 16i minus 6 times negative 1. And what you'll come to notice is anytime I have an I squared, all that serves to do is change this sign, right? Because if we go, well, I have 16I, minus 6 times minus 1 is just plus 6. Oh, I forgot the I there. I cannot leave it in this form. I do have to write that as 6 plus 16I. Although that would be funny if you did mean to put the I'm, Jasmine, because it'd be like, I'm -1. It's a weird thing to celebrate, right? Instead of I'm number 1, I'm -1. Let's look at another one. What if I have 7 plus I times 4 minus I? You guys know that FOIL method? I hate the term FOIL. I really do, because it only works with binomials. I prefer to think of it as distribution, that you distribute the first number to each piece and then you distribute the second term to each piece. Because that way, if I had 3 terms in here, it would still work. So let's look at what happens here. I'd go 7 times 4, and I would get 28. And then I would go 7 times -I, which is -7I. And I've played that 7 out. I multiplied it times both pieces. So I'm going to move on to the next component, which is I times 4. So I have plus 4I. And I have I times -I, which is -I squared. And now we just combine things, right? I have 28. There's nothing to add that to. I don't have any of the real components. I have -7I plus 4I. Well, that's -3I. But now I have this minus I squared, which we just know is -1, right? And so if I simplify that, I get 28 minus 3I plus 1. And so I can add these real components, right? I can combine these two like terms, and I wind up with 29 minus 3I. So not too bad, right? Everything is just like adding, subtracting, and multiplying any binomials or anything with a variable, right? It's just that if we get an I squared, we have to turn it into a -1 and then treat it accordingly, right? I'm trying to see if I've got anything more complex than that, and I don't know that I do. Let's just do one more, just to be safe. So I know I have given you plenty of. What if I have 1 plus 7I times 9 plus 3I minus 4 plus 2I? So order of operations says we have to do our multiplication first. So we're going to deal with all of this first, right? And I'm going to start just like I would normally. I'm going to go 1 times 9. Well, 1 times 9 is just 9. Then I've got 1 times 3I. Well, that's just plus 3I. My 1 has played itself out, so now I'm going to go 7I times 9. What is that, 63? 7 times 9 is 63. Plus 63I. 7 times 3 is plus 21I squared, right? And then this I can just write out. I can go, okay, well, that's -4. And then this is going to be -2I. Now I can start putting things together, right? I go, well, I've got real numbers. I have 9 and -4. Well, that's just 5. Then I can go, okay, well, I've got 3I plus 63i, well, that's 66i, minus 2i, well, that's plus 64i. And then I have this 21i squared. It's positive, right? So all this I squared is going to do is it's going to change this sign to a negative, and I get negative 21. And so I can combine that now with the 5. 5 minus 21 is 16, sorry, negative 16 plus 64i. So that's about as hard as it's going to get. Sometimes you might get problems where it's multiplying multiple things. Like if I had I'm just going to make this up now. So I'm going to try and keep the number simple. 4i times 2i squared plus 3i. And then you'd have to go, okay, well, this is going to give me 8i cubed plus 3i. And if you think about 8i cubed, 8i squared would be negative 8i, or negative 8. Yeah, negative 8i plus 3i. And then we could just add those together and get negative 5i. So you got to play with it a little bit. For the most part, most of your problems will be dealing with this kind of stuff today, because we really contended with this a little bit in the pure imaginary numbers section. So I don't think any of your homework problems today are going to be of that respect. They're going to be more like this, and definitely in the adding and subtracting. You have 10 problems to do. They are all in Delta Math. 5 of them are adding and subtracting complex numbers, and 5 of them are multiplying complex numbers, right? That is your only homework. If you do it, it will take you less than 10 minutes. Get it done. Just go do it. When I see you later this week, we'll talk about division, which is beyond easy, and complex conjugates, which can get a little bit more complex. But none of it's too bad. Any questions about any